Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and it is an honor and a privilege to be serving you and teaching you something as you step into my virtual math classroom. Today we'll be working on graphing functions. I have some practice problems for you, I think 16 total. It's out of a base of 22 and I'm skipping a few because sometimes they become a little more redundant and I just want to get through some of it, of course. What you see behind me, ooh, nice twisty thing, is some little POV roller coaster rides. I last went to an amusement park and I thought that this was the proper setting for it. But anyway, let me just go through the problems right now so you have them. Oh, and one other thing, some people have asked me, Mr. Robinson, why are you bigger on your screen now? Is there a purpose? Do you want to see yourself bigger? No, I upgraded my software that I'm on right now, and for some reason it got me into a trial mode. And it has a big watermark right here behind me on the screen, so I'm just covering the watermark right now until I get that part resolved. So anyway, I hope you don't mind me being just a little bit bigger. Let's go ahead and just get started with the stuff here, shall we? Okay, numbers 1 through 4, we are going to graph each function for the given domain. We have y equals 2x, and we have to go ahead and graph this thing. Now, provided that they tell us that this is indeed a function, it is also, of course, okay that we can use the notation f of x equals 2x. Meaning x is a function, f is a function of x, and f depends on x for something to work, just like y would. And the only reason I'm saying that is because with our domain being just these specific 4 numbers here, we can identify what range values we can get by substituting these numbers in for x to get something out for y. And I want to use the notation to make it just a little more proper. It makes it easier to see. So when I put, for example, f of -2, what I'm telling myself, or this thing here, is that I'm going to be substituting -2 for x, and whatever value I get out becomes the y value when x is -2. So 2x is 2 times -2, which is -4. That means there's a point on my graph. There's a point on my graph that is -2 for x and -4 for y. I'm going to go ahead and plot that point right here, and be careful with the scale. This is -2 right here because that's -4. -2 for x, -4 for y. Plot the point. We're good. That's one single point on this graph. We have 3 more, and let's get them out. We have f of 0, meaning 0 for x. 2 times 0 is 0. We get 0 for y. I can plot that point as well. I'll keep those in green. F of 0 is 0. And then I have f of 2. That's 2 times 2, which is 4. So 2 comma 4. And lastly, f of 4 is 2 times 4, which is 8. So given that they gave me the graphs on this, because this isn't something that I pre-created, these are ones they gave me, they're going to have these things within reason of scale, I believe, and I think it's going to make as much sense to just use their graphs here. Now, a big question in mind here can be, do we connect these dots? Because you can think like, hey, look, they kind of make a straight line right here. Not a perfect line, but do I connect these dots? Well, no, not exactly, because what you have to understand here is your domain. Your domain states the only x values that we can possibly use within our function. And these are the only ones. So within that domain, we substitute those and we get acceptable y values that also represent the range. These are the only points that exist in the function. Connecting a line tells us that we can use any of those points, even the ones between the points, and that's not possible for here. Nor will it be for any of 2 or 3 or even number 4 behind me here. Anyway, so that's how these are going to work out. Let's just keep moving on. Number 2, f of x, or y, equals 1/4 x plus 5, and they give us these values for the domain. Now, as I see this, I'm already liking what they give us because I can take 1/4 of all these values, and they're all integers. And if you have trouble coming up with how to take 1/4 of a value, you simply divide it by 4. So if I'm going to take 1/4 of x, in this case -8, plus 5, I'm going to take -8 and I'm going to divide that by 4. 1/4 of -8 is 8 divided by -4, or excuse me, -8 divided by 4, which is -2. And -2 plus 5 is 3. So there's a point on the graph. I'll keep this in blue, this light blue. There's -8 comma 3, -8 comma 3, and 3 will be in between 2 and 4 like that. That's fine, I'll go and use that, but that is a point on this graph. Okay. F of -4, let's go ahead and get to that one. That's 1/4 of -4 plus 5. I imagine after maybe a couple of these, I might just substitute. No, there's probably a little more we have to do now that I'm looking at the other problems here. 1/4 of -4 plus 5, that's -1 plus 5, which is +4. So -4, +4, just like that. And then f of 0, if you can imagine from the last one, 1/4 times 0 is 0, plus 5 is 5. I think I can speed that one up a little bit more, 0, 5. And then f of 4, is it just the opposite of this? No, but the opposite of 1/4 of -4, which was -1, this can be +1, plus 5, which is 6 right there. So 4, 6. Now again, I do not connect these dots like this, but I want to draw this anyway to give you an idea, or just a heads up of this. What we just graphed in these last two things were both linear functions. And by linear, I just mean that if you did connect the dots, you make a line. These do fall in a linear path right here, and so did these ones. So there are some tips and tricks that you will learn probably in the future when it comes to graphing and understanding that if they keep this rate, can you just find other points to just add on to this? And yes, but because of the domain that we're restricted to, you have to be careful to make sure that you adhere to those x's only. And these are the only x's here. So anyway, so that's it for graphing that one for the given domain. Okay. Number 3, -3x minus 5y equals 20. Same thing with domain here. Now, this time you have two variables. Take it back. You've always had two variables, but this time both variables are on one side of the equation. We have x, we have y, but domain is representing the x values. So I could feasibly substitute values for x and then solve for y each time by doing some things to move things over. What I'm going to do instead to make this a little bit easier on me, and this is a time when I could not say f of x straight up, or I shouldn't. I should only say f of x when I have the dependent variable isolated by itself in the equation. But that's what I'm going to do right now. I'm going to isolate y. I'm going to get y by itself. So I'm going to first rewrite this equation as is. Let's go ahead and add 3x to both sides. I get -5y equals 3x plus 20. Now I'm going to divide by -5 on both sides here. So what's going to happen is divide by -5, divide by -5, and divide by -5. I'm going to do it for all three terms. You have to, but I'm not going to write it as all divided by -5. I'm just going to divide it straight up here. And we get y equals, my first term will be -3/5 x, and 20 divided by -5 is -4, so -4, like that. So I'm going to use this one. I'm going to write it -3/5 x minus 4. I'm going to write that up here, f of x equals -3/5 x minus 4. So now it's just like any of the other ones that we had. Okay, I mean there's another fraction involved. One of the reasons I wanted to do this was so that you know how to use this fraction, because the other one we just divided by -4, but this time there's something in the numerator as well, and like what can you do kind of thing. So let's go and try it. Thankfully, again, they give us good numbers that they can divide by 5. That's an important step, and it's probably the first step I'm going to do. So f of -10, substitute -10 in for x. We have -3/5 times -10 minus 4. Okay, so the -10 technically only multiplies with the -3. And you can then afterward, if you'd like to, divide by 5. There's nothing wrong with dividing by 5 first, though. And what I mean by that is doing -10 divided by 5. Technically, these are dividing. Because these two are multiplying, that means these are dividing. -10 divided by 5 is -2. Okay, these become -2. -3 times -2 is +6. That gets me +6 minus 4, which is 2. So -10, 2, remember -10 for x, 2 for y, is a point on my graph. -10, 2. Now you might have thought that I went through a lot of trouble to create something with a fraction to make this happen, but if you're good with fractions, if you know what you're doing, you'll soon realize this is kind of what's been happening the entire time. And it makes things go faster from here on out. I only have 4 points to do, and one of them has a 0 in it, but for myself, it makes it easier. For yourself, it might be a little more difficult, but I don't know, you wouldn't be watching this video if you thought that you had a way that works well for you anyway. So even if you have that other way, here's another outlet. See if you like it. F of -5 is -3/5 times -5 minus 4. And again, I could multiply these two, but I could just divide these two straight up. 5 over 5 is 1, or let's see, -1 here, -5 over 5. Negative 3 times negative 1 is positive 3. So I get 3 there, and then minus 4, which is negative 1. So negative 5 comma negative 1, that's in between right here, and I guess right here. I'm guessing the graph does something like that. Must have to, based on what I just saw. I think that pans out. F of 0, same kind of thing as before. This turns into 0, and then minus 4 is negative 4. So I got that point right there. And lastly, let's go and divide this a little better. Lastly, I have f of 5, which, to not overthink it, it's going to give me a negative 3 this time. Think about last time it gave me a positive 3 with a negative 5. It's going to give me a negative 3 with a positive 5. Minus 4, that's negative 7. So I get 5 comma negative 7 right there. Those are my 4 points, again going in that same kind of linear fashion, but I will not connect the dots because of my restricted domain. And lastly, number 4, where my big head is, we have y equals x squared minus 3. Okay, this time we have a quadratic. F of x equals x squared minus 3. This is where it's really important that when you substitute, you do use parentheses, especially if you're using a calculator to fall back on at all with these things, to plug these things in. So if I'm doing f of negative 2 to start here, negative 2 squared minus 3, if I write it just like this, and if I ask the calculator, sorry, my nose is scratchy, and if I use the calculator to help me at all with this, it's actually going to give me a wrong answer because I input something incorrectly into this thing. If my x is negative 2, I got to make sure that I square the number negative 2. And if I did this right now, my calculator would just square the number 2, and then it would make it negative. What I have to do is wrap this around parentheses just like I do for any other substitution you've seen. Okay, and then from there, calculator or not, I can do things appropriately. Negative 2, quantity squared is positive 4. 4 minus 3 gives me 1. That's a correct answer. The answer of negative 7, if you get that, is going to be a mistake. It's something that you want to avoid letting happen. If we want this quadratic to work out as planned, then we got to make sure that we write this out correctly. Negative 2 comma 1 is the coordinate pair, again, for this domain. To start off, it looks like we have 5 points this time. F of negative 1 equals negative 1 quantity squared minus 3. Same idea as last time. Negative 1 quantity squared is 1, and then minus 3 gives me a negative 2. So I have negative 1 comma negative 2 right here. Point on the graph. Keep going. F of 0. The zeros tend to be pretty straightforward. 0 squared is 0. Minus 3 is negative 3. Don't even really have to show the work if you can follow along. And you can already start to see right now I'm not going in a straight path anymore. It looks like it kind of bent. This isn't linear. This is quadratic. You are going to be dealing with a different appearance of a graph here. No longer a constant rate. Notice when I square a 2 I get 4. When I square a 1 I get 1. It's not exactly in proportion. 1, 1, 2, 4. F of 1, so this is 1 squared minus 3. Still going to put in parentheses, but 1 squared and negative 1 squared, you can tell you're going to get the same number out here. That's a positive 1. Minus 3 gives you negative 2 again. So even if I substitute a 1, oh, you can't really see that. So even if I substitute a 1 there instead of a negative 1, it looks like I get the same value out for y, which is okay for a function. You can have multiple x's share the same y value as long as no one x can give you 2 different y values, which is of course the whole reason of me plugging these in. I'm only getting a certain number out for this particular number and not 2 different answers. I don't want 1 and negative 7. Only one number is correct, and this one is. But what's interesting here is that I'm getting the same y for a different x, and especially because check it out with this one as well. F of 2. Should that give me a different answer from f of negative 2? Considering the only time that I substitute 2 or negative 2 is when it gets squared and when it turns positive? Well, it looks like we're just going to get the same answer out as this one. 2 squared is 4, minus 3 is 1, just like f of negative 2. So I get 2 comma 1 for this point here, just like I did over there. Kind of interesting, but that is the nature of these quadratics. They turn into these little U-shaped parabolas here. Now it's incorrect for me to connect these. I'm just giving you the overall look of what this thing appears to be when all's said and done. These are the only 5 points I'm going to have for this particular problem, though. I'm sorry, you couldn't see my f of 2 right there. I'm covering it with my big face. F of 2 equals 1. 2 comma 1 was my final point there. Okay, so that wraps up the ones with restricted domains. And by restricted domains, I mean they give us the domain values. We substitute those ones in. But I do want you to pay close attention to the ones that they chose for us, because they gave us nothing but integer answers. Even the ones where there was a fraction coefficient of some sort, we were still able for ourselves to substitute something that gave us an integer y value instead of giving us something really hectic, which we could do if we input them for ourselves. I'm going to try and avoid that for our future problems here in case we run into anything. But let's go ahead and keep going forward. Let's look at numbers 5 through 8, where we just graph a function. This time they don't tell us anything about a domain. They don't restrict us. So generally, if they don't restrict you, what that means is you not only have free choice for what, you not only have free choice for what you want to substitute, but also it means there's no domain restriction. It means that once we plot some points, we should then connect the dots afterward. And I think that's a good goal here. So let's go ahead and do that. I'm going to give 5 points for each problem, meaning 5 inputs generating 5 different outputs. Okay, the important thing is really with the quadratics. Unless you know how quadratics behave, it's good that you at least get 5 points to start to note the behavior, especially if you have the vertex right. I'm not going to get too deep in it, but basically for all the problems, I'm going to choose some negative, some positive, and 0. And based on the nature of some of the problems, like with fractions, sometimes I won't just choose x values that just go up by 1. So let's start with number 5 here. I'm going to go ahead and go in a different format. I'm going to create a table. And same kind of thing as before. I'm going to substitute, only I might do a lot more mentally instead of the other way around. X and y, or should I say f of x? I'm saying it so you're used to it. If you see this here, it's the same thing. X comma y is x comma f of x. Let's choose the basics, -2, -1, 0, 1, and 2. And by default, you'll actually see me do this a lot, especially if fractions aren't involved. Really, you have to think about what you can fit on here. It's possible that I can get a couple more points, and if you really want me to, I can try to. Now I will show one substitution example here for you to be really careful on how you do this, because this time it's x squared, yeah, but this time there's a negative in front. Okay, so what's the whole deal with something being negative as you're doing this problem? Well, check this out. F of -2. Let's substitute -2 for x. What do we get for y? There is a negative that is right here. It is a part. It is a part of your function still. So I'm going to stick the negative there. That has nothing to do with this 2 being negative. Nothing. X is right here. That's where -2 goes. In parentheses, -2. There's a squared and +5. Okay. Negative and negative right here. The opposite of negative is positive, but with order of operations, we don't apply this negative with this negative first. No, 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 no. We do the squaring first. We deal with the exponent. -2 quantity squared is +4. Well, that's great, but there's still a negative that is right here. So remember, I do this stuff first. -2 squared, that becomes +4. But then there's a negative right here. That becomes -4. Okay? That gets a little tricky. I acknowledge it gets a little tricky, but that's a -4 when all said and done. No matter what I do with my numbers, after I square them, they become positive, but then the number goes back negative. So that's what's going to make this problem a little bit different than the previous ones. You may square numbers to make them positive, but now they're going to become negative in the very end. Something's going to change here. Anyway, this equals 1 right here, so I get -2 comma 1 as one of my points. I'll go ahead and keep going green the rest of the way here. -2 comma 1, because otherwise it gets a little, a little different. Let's make the rest of this green as well. Is it that color? Yeah. All right. And I probably, I don't have much room. I'm going to kind of speed some things up here. Let's try this out loud, like verbally. -1. -1 quantity squared. We square it first. Is +1. Take the opposite of that. We get -1. So that's -1 and then +5 right there. All right, which becomes 4, +4. So I get a +4 right there. Hopefully it's making sense what happens there. 0, 0, +5, which is 5. Let me plot those 2 points because I forgot to do the other one. Negative 1 comma 4 and 0 comma 5. Okay. 1. Should 1 be any different than negative 1 based on what you saw in the last quadratic? If the quadratic term is all that remains, if the quadratic term is all that involves an x, and there are no x's that remain in here, 1 squared is 1, we get negative 1 plus 5. It looks like we get 4 again. It looks like there's that, I don't want to give too much away now, but it looks like there's that symmetry involved here, that it seems like when I take some number and square it again, positive or negative, and getting the same result, I can kind of carry on through that problem. For a large part, you can, especially with quadratics. Depends on if there's another x term, though, which there isn't here, and I don't think we're going to get one. It's like kind of basic algebra 1 stuff. But this is all about substitution and what can speed it up. 2 squared is 4, opposite that is negative 4. Negative 4 plus 5 is 1. This is just like the last one we had over here. Negative 2 comma 1, 2 comma 1. So nothing's changing. You can see that. All right, so those are the points that I chose. Okay, I chose those points, and I could do more. You want me to do another one? I'm going to do negative 3 and positive 3, which, by the way, should give me the same number for both. Let's just use 3. 3 squared is 9. Opposite of that is negative 9. Plus 5 is negative 4. 3 comma negative 4. So I'm going to get negative 3 comma negative 4 as well. Same exact reason as I just said before. Okay, I want you to pay close attention to the nature of this graph and these points right here. It is not linear. Again, I cannot draw a line that just goes through these points only. You can see through these points. It's not linear. It's a parabola. It's a U-shaped curve, and furthermore, it's upside down. Now, should I be connecting these points? In this case, yes. Because it's a parabola? No, because there's no restricted domain. Remember what I chose here? I chose them. This problem didn't tell me to. You didn't ask me to. I even recommended 5 points just because, but I chose these points. These points are indicative of any other set of points that I could have chosen within this unrestricted domain. There is no restriction as to what I can choose for x in this problem. I could have chosen 100. I can't fit it on the graph, but I could have chosen 100, or I could have chosen 0.8. The fact of the matter is any x value can be used here to substitute something for y, which means even the points that I didn't choose are included. I'm looking behind me at that wooden roller coaster, a little bumpy. It's a Six Flags something. Six Flags Magic Mountain. Any point can be chosen. So whereas the previous problems when I didn't connect the dots because there were only 4 or 5 such points in the domain, this domain is all real numbers included, so we draw it as such. And the arrows indicate that they keep going. Does this ever go straight down vertically, by the way? No, because I can still choose x values that go this way. They'll go very sharply, very low, but it does curve forever. And there you have it. All right, number 6. I'm going to do it in red, just to have different colors. It doesn't mean anything that it's in red. It's not wrong. I just wanted to let you know that. Well, actually, I'm going to do something first that actually would be incorrect in a way. Not really, but something that you'd probably prefer to go against. 2/3 x minus 1 is the expression for the function here. F of x equals 2/3 x minus 1. Once again, we will freely choose some points. Now, I'm going to write this in red, but all of it's in red. I'm going to write this first, and I want you to act on this a little bit and let me know what you think is up. If I decided to choose these 5 points again, some negative, some positive, and 0, but specifically ones that go up by 1, what is particularly an issue here that you might not be particularly excited about doing? And it has to do with when you substitute x, these numbers in for x, and you take 2/3 of it, what's going to happen? Well, for 4 of the 5 points here, I'm actually going to be getting myself a fraction. And not only a fraction, but something that I have to subtract a whole number from and either try and get a common denominator or work with mixed numbers, and then I have to plot those on a graph that are going up by 2s. Not fun. Not fun for you or I. I like to say that I can do it, but I'd rather say, can I approach this in a better way that deals with numbers that are a lot easier to handle? And the answer, of course, is yes. If we look back at a previous problem here, like number 3, with this 5, notice the numbers that they chose. They chose numbers that were divisible by 5, and 0, of course, always will be divisible by any of your numbers, which I'll keep for my next problem here. But remember when I said that I divided this number by 5, the number I substituted by 5, how this gave me -2, for example? Yeah, the number that I chose should be divisible by 5, and then it'll give me a nice integer. So I'm going to keep that kind of notion for these problems here. For number 6, I'm going to choose numbers that are divisible by 3, because my denominator here is 3 for my fraction, the thing where I substitute something for x to multiply by that. So instead of choosing 1 and 2, I should choose 3 and 6, and even -3 and -6. I think those points are fair enough for what I'm going to do here. So let's just do one of them to make sense of what's happening and then see if you can feel it out the rest of the way. By the way, it's not a quadratic anymore. It's not like numbers automatically turn positive no matter what I do. So f of -6 is 2/3 of -6 minus 1. If you don't know what 2/3 of 6 or -6 is, just go with me. -6 divided by 3 is -2. That's awesome. I kind of wanted that because I wanted an integer. So -2 times this 2 is -4. And -4 minus 1 is -5. So I substitute -6 for x, I get -5 for y. Go ahead and plot that. Okay, so that's kind of what's going to happen. I'm going to take 2/3 of my number and then subtract 1. Of course, you can see that, but I'm going to take my number, divide it by 3, and then multiply by 2. You can multiply by 2 first. There's nothing wrong with that, but I want you to know this other way to do it, to keep your number smaller, number 1. And number 2, to emphasize the fact this is why I chose the numbers, because they can divide by 3. That's the point. That's why I chose these. They can divide by 3, so I shall. I might as well. I'll multiply by 2 after the fact. All right, -3 goes into here. F of -3 for my second bit. -3 divided by 3 becomes -1 times 2 is -2. -2 minus 1 is -3. So I substitute -3 in, I get -3 out. So -3, -3 like that. Yeah, and this continues. I'm just gonna kind of ramble along the rest of the way. Substitute 0. This becomes 0 minus 1 is -1, so that goes here. That's -1. 2 more. 2/3 of 3 is +1 this time instead of -1. Oh, excuse me. 2/3 of 3 is +2. 3 divided by 3 is +1 instead of -1. Times 2 is 2. 2 minus 1 is 1 right here. So 3, 1. And then 6, 2/3 of 6 is +4 instead of -4, if you remember that. And 4 minus 1 is 3. So again, I substituted in values that gave me an integer. I want that, you want that, we all want that. So keep that in mind. Now, compared to the other problems from the page before, I am going to be connecting these dots. So I'm going to be drawing a line right here. Not the best looking one just yet. Let me just move it right there. There we go. That line's going to connect these dots and emphasize the point that I could have chosen. I could have chosen my fraction value, or I could have chosen 1 and gotten an answer, and 7 and 9. And these values will represent anything, any point on this line is a solution to this function here, to this equation. It'll end up working out in that form. Okay. Is that Goliath? That's the right Goliath. Sorry, I kind of just saw it in view. All right, number 7, x plus y equals 0. You know, kind of back to the other thing I did from that other previous problem. Let's get y by itself. Let's subtract x from both sides. We get y equals -x. Kind of interesting here. And in fact, I want you to think about how this works in a table without making the table. Let's try this together. I'm going to choose like all of the problem. Let's choose all the even numbers. See if this will make sense to you. It should. See if this will make sense to you. Let's start with 0. I substitute 0 for x. What do I get for y? -0. But still 0, right? Let's plot that point right there. Right there. Plug in 2. Y equals -2. Oh, y equals -2. right? So that's kind of what I'm doing right now. When x is 2, y seems to be negative 2. When x is 4, y seems to be negative 4. Is this kind of making sense? Y is the opposite of x. That's literally what this equation is telling me. It's the opposite of x. Plug in 6, I get negative 6, 8, negative 8, 10, negative 10. 5, negative 5 if I really wanted to, but landing on the crosshairs here, it's as simple as it gets. Now, if I go negative territory, what's the opposite of negative 2? Well, that's positive 2. So when I go negative 2 for x, I get positive 2 for y, and there is that point. And so on and so forth. See, this is linear. It continues on this same rate path, and it keeps going in this direction with it's what's called a negative slope, if you will. I don't know if we're on that stage yet together as a virtual class here, or as a class in general, but there's the line that connects those points. Remember, no restricted domain. I chose these numbers, could have chosen anything else. That is the path that it goes on. No table needed. I went ahead and found a way without it, and it seemed to work out. Okay, one more problem, number 8, and this one I probably will have to use a table for instead. It's just, there's a little more to it. This deals with not only a quadratic, but also a fraction. But what we saw with fractions last time is if we choose numbers that are divisible by the denominator of our fraction we're talking about, and that's a good first step. And also what we learned is that for quadratics such as these, when that's the only x that's available, your negative squares will turn positive, like your positive squares will turn positive. So as long as I know what numbers I choose in the positive realm, I should choose the same thing in the negative realm, and it looks like they'll get the same height. So like if I substitute 7, I get some y value. If I substitute negative 7, I should also get the same y value. So I'm going to kind of play with that notion, and I'm going to try and only use 5 points again. 0 is going to be one of them. Let's go ahead and use this color here. So I used that color. That's right, I kind of used all the colors already. 0 is going to be one of the numbers. 1/4 of 0 squared, that's 0. Okay, minus 8 is negative 8. So 0 comma negative 8 is one of the points here. All right, the other points that I want to choose have to be divisible. I want to make them divisible by 4. Now keep in mind, I have to square the number first. And as long as that number is divisible by 4, then I'm good. So you might think, because I want to choose 2, but you might think, wait, 2 is not divisible by 4. I agree, 2 is not divisible by 4. But if I square 2, it does give me a number divisible by 4. Good news is, any even number that I square, any even number, I don't know if I'm saying this right, it should be divisible by 4. Starting with 2. 2 squared is 4. Check this out. 1/4 of 2 squared minus 8. We're talking about f of 2 here. I'm going to first do 2 squared, right? You square your number first. So that becomes 4. So we're going to take 1/4 of 4 minus 8. 1/4 of 4 is 1. 4 divided by 4 times 1. So that's 1. Minus 8 is negative 7. So I substitute 2 and I do get negative 7. That's kind of cool that I can use that number and work something out to an integer. See, if I substituted 1, I'm going to get an odd number, and no odd number is divisible by 4. In fact, all the odd numbers that you square will become odd. So I'm only going to choose even numbers here. And like I said, even numbers will be divisible by 4 after you square it, which is great. We'll use that. Before I do that, if 2 gave me negative 7, what will negative 2 give you? Think about what we did before. Negative 2 squared is the same thing as 2 squared. It's also going to give you negative 7. So both of these go in there. Hopefully that's making some sense there. I'm going to substitute 4 now. 4 is divisible by 4, so 4 squared better be divisible by 4 as well. 4 squared is 16. 16 divided by 4 is 4. Minus 8 is negative 4. So I'm going to go ahead and put a negative 4 here as well, and that should also give me negative 4, just like 4 did. Because I think I can fit some more points, I'm going to do just one more. I'm going to do 6. 6 squared is 36. Divided by 4 is 9. 9 minus 8 is 1. And negative 6 will also give me 1. I could probably fit more. I'll even plot the other points because I think I know where they go. Because I want to show you as U-shaped as I can get with this one. Because it's 1/4, I do like the trend that this thing goes on. It's going to be a wider looking U-shape. A wider looking parabola than even the previous ones that you saw. 4, negative 4, 6, 1. Negative 4, negative 4, negative 6, 1. Right there. If I substituted 8, I would get You know what? That'd be too large for this thing, I think. No, it shouldn't be. Wait a second. Substitute 6, I get 9. Oh, right, because you subtract 8, right? So I substitute 8, I'm going to get, I think 9. Wait, let's do that really quickly. 8 squared is 64, divided by 4 is 16. Oh, minus 8 is 8, excuse me. I'm going to get 8. So I get 8 right here. 8 and 8, negative 8 and 8. Couldn't fit it on the table, so I'm not going to draw this very well. I'm going to try, but here's your U shape this time. Oh, wait, messed up. Just deal with it. But connect the dots, kind of go as smooth curve as possible here. Not bad. Check out that parabola. Okay, I like that one. I'm proud of it. So there's my U shape for that one. Looks pretty good, but I am getting short on time here, and I still have 8 problems to go. I think they go faster now, though. It was all about plotting the points. So there's my domain for those problems there. So now you're hopefully getting the good gist of choose your points for inputs if they don't give them to you, but choose very wisely. It depends on what you're trying to get. Notice I always did some negative, some positive, and then 0 as well. I'm trying to think of what roller coaster ride that is. That might be Viper. No? Oh no! You know what? That's a boomerang ride. I don't know what it's called. It's some boomerang ride. All right. I said I gotta be time conscious. Let's go and move on. Use a graphing calculator to find the value of f of x when x equals 3 for each function. No graphing calculator. Let's just jump straight into it. Find f of x when x equals 3. That's really just asking you to find f of 3. That means substitute 3 for x to find out y. You know, it's kind of interesting how these problems ask you to just use that, probably because they want you to practice the graphing calculator portion, but I'm just going to go ahead straight up and substitute. 3 divided by 3 is 1. Remember, they do divide. Times 1 is 1. 1 minus 2 equals negative 1. So again, that means that when I substitute 3 for x, I'm getting negative 1 for y. That is the end result. That is a point on a graph for this function. Okay, not that we're graphing it. Now substitute 3 into here. F of 3 equals negative 3 quantity squared minus 4. And remember how the parentheses this time, I'm only squaring the number 3. I'm not squaring negative 3. I'm squaring 3. 3 squared is 9. The opposite of that gives me negative 9. So negative 9 minus 4 is negative 13. Order of operations are so crucial for problems like these because you can really make the mistake of, squaring a negative to make it positive when it shouldn't be, because that negative exists on the outside. This thing has some sort of type. This should say f of x, just like the other ones. Use a graphing calculator, find the value. Okay, so same kind of thing. This time substitute negative 4. These problems are relatively easier than the previous problems. We're asked to do it once, and then they're not asking us to graph. Well, of course, they are suggesting we use a graphing calculator. I'm going to refrain if that's totally cool with you. So f of negative 4 equals negative 4 quantity squared minus 3. Look at that. Substitute. Use the parentheses with negative 4 here. Negative 4 quantity squared is 16. 16 minus 3. I'm looking at the ride. 16 minus 3 is 13. Is that? Sorry, I have a screen over here as well. I think it's x2. It was called X at first, and then they repainted it, did some different things. Now it's called X2. Yeah, that's X2. Sorry. All right, f of negative 4 for this one. Negative 4 times negative 4 minus 3 halves. Okay, so this time we unfortunately have to deal with the fraction, but you know, it works. Negative 4 times negative 4 is 16 minus 3 over 2. 16, I want to write that as a number as something divided by 2. 16 is divided by 1. I want to get a common denominator, so I'm going to multiply top by 2 and bottom by 2. 2 times 16 is 32, so I get 32 over 2 minus 3 over 2, which becomes 29 over 2. I'm going to leave it like that. I'm always fine leaving fraction things like that as improper fractions. The one thing though is if you had to graph this, it would be better to actually divide it and figure out what it becomes. So like if I graph it, where is 29 over 2? Well, it's 14 and a half. So you'd have to know where to plot that point. But as far as writing the answer, if this was in a table, I'm good with that. Like personally, and your math book or your math teacher would be as well, especially depending on what you're doing here. All right, there used to be a number 13 here. I'm actually skipping number 13, going straight on to number 14. The rest of the numbers, I think there's 14, 18, 20, and 22. I'm only saying that because if you think that there's something missing in the video, you didn't miss anything. I skipped them. I'm only doing so many problems here. All right, number 14, graph this function and then find the value of f of x when x equals 1/2. So this thing kind of comes in two forms here because they're asking you, and this might be why they asked me to use the graphing calculator before. They were probably asking us to, yeah, that's probably what they're asking us to do. Go to the graphing calculator to graph the function and then look at where it lands on there. Now, I wasn't particularly interested in pulling up the graphing calculator for this very bit because I would have to do a lot of syntax stuff. I'd have to pull it up. And I wasn't going to hand draw the graph, but this one's ready for me to hand drawn by instruction and because it's prepped. So I'm going to do that first. And then we look at the graph and we'll look at what the f of 1/2 is, what f of 1/2 is. It's asking you what is the y value there. So I'm not going to substitute 1/2 in for x in this. I'm not going to, at least not from the beginning. I'm going to choose my -2, -1, numbers like that. I'm seeing with this problem, it might not be wisest to choose those numbers, and you'll see why in a moment. But let's go ahead and get it started. All right, so -2, -1, 0, 1, and 2. And start with -2 here. 8 plus 2 times -2 is -4, so 8 minus 4 is 4. 8 plus -2 is 6. Hopefully you're understanding what I'm doing. It's substitution. 8 plus 0 is 8. I was about to say 0. 8 plus 2 times 1 is 10. And 8 plus 4 is 12. Most of these are plottable, and by plottable, I basically just mean that I can fit these on the graph itself within the window that's given. I can't fit this last one, though. You can tell it's a little out of range. And just to be consistent with plotting 5 points, it looks like if I go farther positive on x, I'll go farther positive on y to an unreachable amount. So let's go this way instead. Let's choose -3 as our next point, because why not? 2 times -3 is -6. 8 plus -6 is 2. So I have -3 comma 2, which is a nice fifth point there. And I got to connect this graph for the very reason I was talking about before. We're not restricted in our domain, and we have to account for every particular value that may be used here. So that's decent as a line. Let's get a little more decent, just like that. And this is important because for this graph, and this graph isn't very decent for us, but for this graph, we have to be able to use the graph to find the value of f of x when x equals 1/2. Okay, and again, I'm not particularly proud of this thought here because of the scale of this thing and that they gave us a fraction value. But what they're asking you to do is this. Here's 2 for x. Here's 1 for x. Here's 1/2. Here's x equals 1/2. They're asking you, what y value would you get if you substituted 1/2 for x? And again, I'm not proud of being able to do this given the limited range that we have, but what would we have? So on 2, we had up to 12. I guess it was all the way up here if you really wanted to count it. If you substituted 1, as we did, we would get 10. And when we substitute 0, we got 8. 1/2 seems to be drawing all the way up right in between that 8 and that 10. To what value? That one right there, which is between 8 and 10. And because of the proportionality, that linear rate here, if 1/2 is halfway between 0 and 1, then its y value is halfway between 8 and 10. It's going to be 9. F of 1/2 is 9. And if you're not convinced just yet, let's do that together. 8 plus 2 times 1/2 equals 8 plus, what's 2 times 1/2? That's 1. 1 equals 9. So yeah, we get 9 regardless of the way that we kind of substitute it there. And if I gave my students a test on this kind of thing, I'd make sure that they could see the 1/2 a lot better on there. I'd probably ask them for what's f of -4, which is 0, something like that. But as long as they draw it right, then all is going to work out just fine. All right, moving on. I got 3 word problems here the rest of the way, just some graphing and some more estimations like they're asking here. The total cost of a cab ride can be represented by the function f of x equals 3x plus 2.5, where x is the number of miles driven. Now they say total cost. That's saying it can be represented by the function. That means total cost is f of x and x is miles driven. My input is the miles driven. My output is the total cost. Meaning I can figure out how much something costs by stating how much I've ridden, righted. Graph the function, use the graph to estimate how much the cab will cost if the cab ride is 8 miles. Okay, so this one right here, what's kind of nice that they used for us is increments of 2.5. You can see the 5 right here, which means halfway is 2.5. Kind of nice because of the 2.5 right here. You know, I kind of want to use that. What I don't like is this 3, and you'll kind of see why. I'm going to start off a table and get this understanding, more established by choosing numbers. Notice I'm not going to choose any negative numbers anymore because the way that they give us this graph, it's only a first quadrant thing. You can't drive negative miles, right? So there's nothing negative to be had there. If I substitute 0 for x, though, 0 miles driven, 3 times 0 is 0, plus 2.5 is 2.5. This is one of the points on the graph right there. And this is for the cabbie. Now, here's the thing. If I start to choose, and look, there's 1 and 2 and 3, etc. If I choose 1 for x here, I'm going to get 3 times 1 is 3, plus 2.5 is 5.5. I mean, where is 5.5 on here? You know, this number here is 7.5. 5.5 is a fifth of the way. If you don't know this, it's a fifth of the way between 5 and 7.5. Is it really realistic for me to be able to plot that point right there as is? Probably not. And for the sake of this problem, I'm going to avoid doing that. What I'm going to do instead is find the next number that could potentially land on this thing to graph. I might put in some of these values, but you'll start to make sense how we do this in a faster way. If I try and use 2, 3 times 2 is 6, plus 2.5 is 8.5. Okay, that's still not on here. Remember, this is 12.5, this is 17.5, this is 22.5. I'm trying to find one of these numbers again. This is 27.5, and this should be 30. Okay, 3 times 3 is 9, plus 2.5 is 11.5. But do you notice what's happening on the y values? Every time I increase x by 1, it looks like y is increasing by 3. Now, this is an important note because that 3 is this number right here. Every time I increase x by 1, I'm doing 3 times another number. 3 times 1, 3 times 2, and 3 times 3 just states that I'm adding 3 one time, or 2 times, or 3 times. So every time I multiply 3 by the next number up, I'm just adding another 3 to my slot. So I do kind of know, instead of having to type that in or like calculate that each time, all I got to do is add 3 each time. So let's just do that. Let's do 4. 11.5 plus 3 is 14.5. Still not on there, but that's kind of the goal. 5. 14.5 plus 3 is 17.5. See, 17.5 is on our graph. So I'm going to use 17.5 here. 17.5 for 5 goes right there. Okay. Now, I only actually need 2 points to plot a line. Remember, this is linear. This is a line here. So I'm just going to use those two. I think if I went another 5, I'd go a little out of range. But my goal, my understanding is if I go another 5 over to 10, let's see what it is. 2.5, or sorry, excuse me, 10 times 3 is 30, plus 2.5 is 32.5. So that is a little bit out of range. It would probably be the next one up right here. Probably close enough. I could try that. But that's a graph for my cabbie. And yes, I could conceivably have done this with all the other numbers, but I don't want to go to those fifths. You know, I want to stick kind of to this thing here. I'm going to use a single arrow here, not a double arrow, because I want to imply that I can only go one direction on this thing. I can't go into the negative territory. So I'm going to stick with that. Looks like it didn't quite fit the bill. Yeah, it's close enough. So there's my graph there. Now, do I connect these dots? Absolutely. I can drive 1 mile in the cab or 1.7 miles in the cab. All of these miles can be driven in the cab, and they're going to give me the cost based on that. So they say use the graph to estimate how much the cab will cost if the ride is 8 miles. So I kind of do like that I only used the 0, the 5, and the 10 here, because now it's showing that I'm not just going to substitute it in. They say use the graph to do it. So let's try that. A straight line up from 8, x equals 8, right? 8 miles on x, is f of 8 equals what? What value for y with x equals 8? I go up, up, and I land about right there. If I if I said it's halfway between 25 and 27.5, I guess you could be on that way. If you've recognized, and this is a guess, I believe I'd be right by saying this. I don't know for sure. But remember last time I said that these go up by fifths. The first one went by 1/5. That's probably 2/5 and 3/5 and stuff like that. So my imagination or my guess is this is either the 2/5 number or the 3/5 number. And actually, now that I'm looking at it, now I know which one's supposed to be. What I meant is 3/5 of the way between 25 and 27.5. If you said somewhere in the 26 number range, I'm sure you'd be fine. I'm going to put approximately equals. I know what the actual answer is. It should be 26.5 because it's 3/5 of the way from 25 to 27.5. I add a couple 0.5s. That's going to be the answer, but also it is a cost question. So it costs $26.50 to ride this cab here. One other thing I want to mention here, just at the very end, just to make sense of all this, was the 0 miles driven and $2.5 spent. Keep in mind with the cabbie here, they give you kind of an upfront cost to really make you want to stay in there longer. They're trying to promote the idea that if you drive short, I'm still going to charge you a little bit for having just gone into my cab. Because you've taken time to do that, and you've taken up time to for me to see another customer or whatever. You can enter that cab, you can hail the cab down, flag him down, put your stuff in the back, whatever it is, ask to go somewhere, and just as he's about to leave, you go, wait, you know what, I decided someone else is going to pick me up. I decided to walk, whatever it is. I decided your cab stinks, and you leave. They're probably going to charge you because you just took up their ability to see somebody else, to get another person in their cab. They probably lost a customer, and you took up their time. Pay them $2.50. It's just part of it. All right, I'm just going to move on to 2 more word problems here. Same kind of deal. The production cost for G graphing calculators, see that's a number. G graphing calculators is C of G equals 15G. This is like your Y and your X. It's your input, your output. They even tell you right here, Y and X right there, C and G. So treat it like that, dependent, independent. If you buy this many graphing calculators, it'll cost you blah, 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 this much. They should really say scientific graphing calculators. I don't know, a graphing calculator is only $15 per. Graph the function and then evaluate it when G equals 15. What does the value of the function at G equals 15 represent? So I kind of talked about it before. Let's get this fully sorted out. Again, not a big fan of what they're... I take it back. I am a fan of what they gave me. But I do have to base what I do on what they gave me here. Because you can see the increments. Graphing calculators. You see how this is a 5? Halfway there is 2.5. I am not looking toward finding out what the cost of 2.5 graphing calculators is. That is not of concern to me, or to you, or to anybody. You can't pay for 2.5 graphing calculators. You can pay for 1, 2, 3, 4, 5. You can't pay for 2.5. I'm sorry, we don't have X on here. But what I'm going to do instead is really adhere to the ones that I can fit on here easily, meaning these numbers. And the good news is, as I did it in my head, the numbers that I choose here, I think will give me clean crosshair values I can place on here. 5, 10, 15, and 20. So I'm going to substitute 5, 10, 15, and 20. I have a lot more room than that, my bad. 5, 10, 15, and 20. I substitute 5 in for G. 15 times 5 is actually 75. And yes, 75 is between 50 and 100 right there. I substitute that, I get that. By the way, another one I'm going to plug in is 0. I plug in 0, I get 0. I buy 0 calculators, it costs me $0. That makes sense. They're not going to say, well, you got in my cab first and you stole another customer from me since you put it on the checkout. It doesn't work like cabs that way. 10 times 15 is 150. So I'm going to plot that one in right there. You can kind of see this growth. Every time I go up 5 calculators, it looks like I'm going another $75. So 15 is going to cost $225. That's 150 plus 75, or 15 times 15. And the last one doesn't even fit, so I'm not going to worry about it. But that one's right there. Now, do I connect these dots? Well, no, because the thing that I said before, you can't buy half a calculator, so I can't just make this big connection here. But I'll be ashamed to say that I am missing some calculators on here. What about if I buy 1, 2, 3, or 4? They're not really on here, right? They would probably look something like that, and I'd probably have to, put them in like that. So a realistic graph using integer numbers of calculators would look like this. You can kind of leave those off if you absolutely need to. But evaluate this when g equals 15. So c of 15, it looks like we already got that. That's 225. And you can see that on the graph right here. 15 goes to 225 right there. They said, what does the value represent of the function? G equals 15 represents 15 calculators. What does c of 15 represent as 225? That is the cost of 15 calculators in dollars. 15 calculators cost $225. That's my guess. We don't have dollars on here, but they did say cost. So, oh, production cost, not sales cost. That production cost. No wonder. I was saying graphing calculators don't cost $15 each. I should read the question a lot more, a lot more deeply. All right, I'm almost at an hour here, so I'm cutting this off right here. Number 22. A snowboarder's elevation in feet can be represented by the function e of t equals 3,000 minus 70t, where t is in seconds. Graph the function and find the elevation of the snowboarder after 30 seconds. I'll ignore that part for now. I'm just really looking at this bit here. Very nice scale. You can tell this one's way different. It would be hard to do this with a graph on your own. So let's take a look at this. T is in seconds. So 0, so we'll do a horizontal table this time. 0 seconds in, the snowboarder is at the elevation 3,000 feet. I mean, that's the whole ordeal here. After, it says snowboarder's elevation can be represented by this. So after 0 seconds, it hasn't changed elevation just yet. So this is t and e of t, x and y. I substitute 0. Look like these go up by 5s. And 70 is an interesting number here because these go down by 500s, and none of these really, 70 doesn't really hit the 500s. So I'm gonna have to do my best approximations here, and I will. I'm gonna just substitute the first 4. I'm kind of running out of time here, so I'm gonna use the first 4. 5, 10, 15, 20. That's fine. We're gonna estimate this. We'll find the elevation after 30 seconds. Let's estimate this one. Substitute 0, you get 3,000 minus 0, which is 3,000. So 1 point I can get is right here. Oh, looks like it doesn't even hit these points here. Substitute 5. 70 times 5 is 350. 3,000 minus 350 is 2,650. So it's more than 2,500 still. And it's not quite halfway. That's 2,750. So 2,650 is probably about right there. Again, I'm doing the best I can. 10, that's 700. 3,000 minus 700 is 2,300. One thing I do know for sure, though, is it does go at a constant rate. 2,300 is 3/5 of the way to 2,500, so it's probably ish like that. Get a little higher up there. There we go. And then 15, 70 times 15, ooh. 1050. 3,000 minus 1,050, that is 1950. So 1950, very close to 2,000 here. Very close, so put it right up there. And then 20, 70 times 20 is 1,400. So 1,600 right here. Okay, so 1,600, it's 1/5 of the way up from, whoops. Yeah, it's close enough. Okay, so I'm going to go ahead and graph a thing here. It's my last graph. And remember, I didn't get all the way to 30. I'm plotting the points as best as I can. I'm going to approximate this one. You know what I mean? I think it's pretty good. The snowboarder is probably not going to crash through the ground, but if the snowboarder continued, you can see it looks like it would probably hit the ground after 45 seconds. Snowboarder's going down very fast, it looks like. Less than a minute's time. It goes from 3,000 to there. It's like it's free falling. Jeez. Okay, 30 seconds. What is it at, after 30 seconds? That's when t equals 30. What is e of 30? What is the elevation at 30 feet? Here's the 30. Go up here. That's probably around, it's between 500 and 1,000, a lot closer to 1,000. Probably a little around 900. Probably 900-ish. 950, 925, I don't know. Well, it's with 70s. Probably around there. That's using the graph to do that. But if we substitute 30, let's go and see what it is. 70 times 30 is 2100, so 3000 minus, ooh, yeah, 2100 is 900. So yeah, it's going to be 900 feet right there. That answers that last one. So again, these graphs are kind of a little too big, like a little too generalized for us to get an exact number and hit it there, but that's what we're doing. Use the x to find the y. Sometimes they'll use the y to find the x. They'll say the snowboarder was at 1,000 feet, how many seconds into it? And you could say the same thing. Oh, 1,000 feet, it's at like 28 seconds, something like that. That happens too. Okay, I've run past this course. It's been an hour now, so I am all wrapped up here. Thanks for watching, guys, and sorry to take your time. I tried to cut it a little bit short. Didn't quite work. Hope you enjoyed some roller coaster videos behind you. Have a good day.